Hello, everyone. Nice to meet you in the afternoon. I am Jingfeng Wu. I just graduated a few months ago from Johns Hopkins University, and currently a postdoc at Simons in the ML research pod. So today I'm gonna talk a little bit about my research and a few problems in deep learning theory. Specifically, I will be talking about large-stepsize gradient descent. So a few words about my research interests. I'm interested in deep learning theory. In particular, I'm interested in the intersection between statistical learning theory and optimization in the context of deep learning. To be more specific, so deep learning has revolutionized the practical machine learning, and on the other hand, it also revolutionized our understanding of the learning theory itself and optimization. So that's why I'm very interested in the theory of deep learning, and in particular, I'm interested in some topics like how to learn a over-parameterized model, meaning that the number of parameters in the model is even larger than the number of samples you have. Can you still do learning theory in the setting? And also, I'm interested in algorithm regularization. In fact, like how an optimization algorithm, the procedure you learn, the procedure you train the model can provide some regularization effect that can help you to generalize in the over-parameterized setting. And in particular, I'm very interested in studying gradient descent algorithm and the stochastic gradient descent algorithm. Yeah, in today's talk, I will be focusing on gradient descent, a very specific problem in these topics. Okay, so in case of people here are not familiar with deep learning, let me briefly go through the high-level idea of deep learning. So what is deep learning? It is just some new arts of fitting data. So let's say I have an image. I know its label. I think this image should be dog instead of glasses. So what I do is like I come up with a very flexible model, okay? And then I'm gonna tune the parameters in this model such that the output of this model make the same prediction as I wanted it to be. Okay, then I repeat this procedure for tons of data, okay? Hopefully this model, after seeing so many data and its label, hopefully it can generalize on an unseen new data. So that's pretty much the high-level idea of deep learning. And so how do we feed this data? In specific, the common recipe is to do gradient descent. Okay, it's a very old-fashioned algorithm. Dates back to Cauchy in 1947. So the idea of gradient descent is very simple. I grab a data and its label, and then I ask my model to make a prediction about the data, okay? And then I calculate the distance between the current model prediction and the targeted label. And then I make an update about my model according to the negative gradient direction. So this way I'm guaranteed to descent the distance between my prediction and the target label. After repeating these procedures, hopefully I will find a good model that can fit all of my data. Okay. So yeah, this is very nice, and the gradient method has been used in pretty much every current deep learning model. Pretty much everything is trained by gradient descent or its variant. But why this algorithm works so well? This problem is far from being fully understood. So today I'm gonna focusing on one specific mystery about gradient descent. That is how to choose the suitable step size in gradient descent. Okay, so when I introduced the gradient descent method, I actually missed a very important recipe. That is in step 4. When we want to make an update of the model along the negative gradient direction, how much update should we make? Okay, so Okay, so in other words, what is the step size should I choose in the gradient descent update rule? Okay, let's first ask this question to a theoreticians. Okay, what a theoretician will do, it will the theoretician will run some equations. Okay, let's say our model is parameterized by W, and we have bunch of data, and then we can write down a objective. Now we want to find the W such that it minimizes this objective, okay? And then we write down the gradient descent update rule, and then let's do some math. Let's plug in this gradient one-step gradient update to our objective, and then let's do a Taylor approximation. Then you find that, okay, if the step size eta is small enough, then the green box is a positive quantity. That means every time you run a gradient step, you are guaranteed to decrease your objective by some amount. Okay, and okay, this is very nice. Then I can write a theory paper, and it has a theorem says that if the step size is small enough, then L of WT will decrease monotonically, and then I proved that gradient descent will work. Very nice, and I get a theory paper. So okay, this is very nice. Then let's try again. Ask this question to a practitioner. Okay, what a practitioner will do, it will run some numbers. Let's do a very simple naive experiment. Let's just try a very simple fully connected neural network. Okay, and grab 1,000 samples from a very simple data set at least, and then let's use gradient descent to fit this data set. Okay, let's conduct some experiment. You see, you see the green curve represents the loss of gradient descent with a small step size. The red curve represents the gradient descent loss with a large step size. Okay, so it seems small step size works, but the large step size also works, and even it works even better in the long run. Okay, so then, sorry. Anyways, so then you see there is a gap between the. Oops. Some of my slides is skipped. Yeah, then you can write a deep learning paper. Okay, you claim that the large step size works better, and why? Because I tried 3 different random seed, it all works better than small step size. This is okay. Then you get a deep learning paper, but there is a huge gap between the theory paper and the deep learning paper, right? You see, the deep learning paper tells you should run very large step size, and where the loss actually can oscillate, but it works in the long run somehow. But the theory paper says that, okay, you should do small step size where you are guaranteed to converge. But and moreover, you can run a minimax. Probably the theory paper will contain a minimax result. It will construct a hard example such that in the worst case, if you do a large step size, you will diverge. The loss will never converge. But these two things seems to be there's a huge gap between what happens in deep learning and what the theory people will tell us. So what can we do to fill this gap? It turns out there's no contradiction. Just that the existing theory, what we known before, does not explain what happens in practice. Okay, so it's actually there is a very simple fix to the theory to cover what happens in practice. That let's say let's make some assumption to make our life easier. Let's assume the neural network is very simple. It's just a linear neural network, one layer linear model. And let's assume the data set can be perfectly fitted. Then it can be shown that if you run gradient descent with any constant step size, you can still converge. Despite that, the risk might oscillate in the beginning. It will converge in the long run. Okay. So why this happens? The intuition is that the loss landscape is not quadratic at all. because we are using logistic, we are using cross entropy. We never use, it's a classification problem. That allows us, so let me show you a cartoon about the loss landscape. So loss landscape more likely will be a open valley where along one direction, the loss will decrease monoton. Go along one direction, you will decrease the loss. But along the other direction, the shape is like a quadratic thing. So when you run gradient descent with a large step size in this loss landscape, there will be two forces fighting each other. One force drags you down the valley. The other force causes oscillation along the decreasing direction. So when the other force wins against the force that drags you down, then you observe a risk increasing. But eventually, the effect of the force dragging you down, this effect will accumulate along the optimization iterations, but the other force will cancel each other, their effect. So in the long run, large step size gradient descent can still go down the valley. So yeah, that's pretty much the intuition. And regarding the question, I in the beginning of the talk, I claimed that I wanted to study how to choose a step size, but it turns out I haven't answered this question. I just showed that okay, you can run large step size and you can still converge, but why large step size works better than small step size? This is still an open problem until now. So that's all. Thank you.
Any questions yet?
So just to be sure, the last plot says something about numerical instability, or you say that eta equals 10 in a model that this is a non-convex optimization in some training. Is that correct?
This plot is convex. This is for linear model.
Okay.
The prior
plot is okay. And so you say that for eta equals 10, this is your opinion is that this is numerical instability, or there is some theory that should explain that?
Yeah, I think so. The conjecture is that if you if you are allowed to run 200 iterations of gradient descent, then you should do a very large step size.
I see.
But if you're only allowed to run 10 steps of gradient descent, you should use small step size.
Okay, thanks. I got the point.
Yeah.
Any other? Yeah.
How much should you rely on just this linear assumption? Is it explanatory for more complex loss functions? What is the take? I mean, it's too simple in some ways, maybe.
Yes.
How much can you generalize?
Good question. How much I think the intuition in this picture should be generalizable, but the analyze techniques needs to be reduced.
So even for quadratic, there's no proof.
For quadratic large step size, it doesn't work because it will be probably divergent. That's a hard case in the optimization theory. But it turns out that in deep learning, because you are all over-parameterized, there pretty much always exists a direction where you can go along that direction to further decrease the loss.
So what would be the next model to study mathematically after linear? Do you have a candidate?
I mean, this model is still linear, but just the loss function is not quadratic. It's like a cross entropy type.
GLM could work, for example.
Okay.
Yeah.
Yeah.
In sort of the classic econometrics literature, if I have more parameters than I have observations, then there's no closed form for even just a linear model like this.
Yeah.
Whereas my understanding of this is that, so long as I use gradient descent and any constant step size, I can get the true parameters from a linear case. Am I understanding that correctly?
Yes, this theorem says gradient descent will find the optimal parameter. What's your question? Can I say again?
I guess I'm just saying, like, it feels very counterintuitive to me to be able to get exactly what the parameter values are when I have more parameters and observations, because, you know, the classic result from econometrics is that,
Oh,
you know,
I see your question.
I don't, if I have more parameters and observations, like,
Yeah,
I
okay.
can't identify them.
Yeah, okay, I see your question. So the global minimizers are not unique. There exists a set of global minimizers, but the loss induced by the global minimizers are the same. So gradient descent will find one of them in that set.
Okay, well, thanks a lot. Okay, so next, Emmanuel